Momentum, often represented by the letter P, is an abstract feature an object has due to its mass and its motion. An object's momentum is equal to its mass, multiplied by its velocity. It can be loosely thought of as a measure of how hard it would be to stop the object if it were thrown toward you. The faster or more massive the object is, the harder it would be to bring to rest. An object at rest has no momentum. A basketball has less mass than a bowling ball, so if they were moving at the same velocity, as shown in the left illustration, the bowling ball would possess more momentum. However, if the basketball were moving fast enough, it could have more momentum than the bowling ball. A very deep characteristic of nature is that, given the absence of any external forces acting on an object, its momentum is conserved. We are assuming here too that no mass is being gained or lost by the object. This is a deep and mysterious characteristic of nature, though it can be expressed in a variety of ways, and it can be related to properties of space. We have no explanation as to why momentum is conserved. Angular momentum can be thought of as the rotational or revolutionary counterpart to momentum. Objects that are rotating on their axes or orbiting around other objects possess angular momenta. The discussion is easier to follow if one considers an object moving around in a circular path, as shown. The angular momentum of an object, with mass m, is equal to its mass times its speed times its distance from the point about which it is orbiting. Here v represents speed and r represents the distance. In the absence of an external twisting force, or torque, angular momentum is conserved. If we assume mass doesn't change, this conservation law can lead to some interesting behavior. The illustration on the left is of an ice skater with her arms stretched out. There is a certain distance out to her arms. She will then push off the ice once to get herself rotating. We will assume there is negligible friction between the ice and her skate blade, so there is no external torque on her body. If there is no external torque, then her angular momentum will be conserved. When she pulls her arms in, the distances from her arms to the center of her rotation are decreasing. Since angular momentum must be conserved, her rotation speed must increase. If she were to put her arms back out, she would slow back down. Similar physics is involved when doing somersaults on a trampoline or off a diving board. We are equipped to have a deeper understanding of Kepler's second law. Imagine a line drawn from a planet to the Sun. As the planet gets closer, its speed has to increase enough to conserve angular momentum. As its distance increases, it slows down. Kepler's second law is the result of the conservation of angular momentum.